This webinar is sponsored by NEC Corporation, a $37 billion global technology leader with over 100 years of innovation to empower people, businesses, and society. NEC's ProgrammableFlow Network Suite, the subject of this webcast, was the first commercially available enterprise-class SDN solution to leverage the OpenFlow protocol, enabling complete network virtualization and allowing customers to easily deploy, control, monitor, and manage multi-tenant network infrastructure. In addition to simplifying network administration, NEC provides a programmable interface for unifying the deployment and management of network services with the rest of IT infrastructure. Thank you for your time and interest in NEC's ProgrammableFlow Network Suite.
This sponsored webinar is one of many IP Space Data Center webinars. You can register for live sessions, buy the recordings, or get access to all of them with a yearly subscription. For more information, visit ipspace.net/DC. Welcome again, and the topic of today's webinar is NEC's ProgrammableFlow, and we'll try to go as deeply into the product and feature set and all the dirty details as you wish. And to keep me honest, I have Samrat with me on the webinar. And Samrat, please tell us what you're doing at NEC.
Hi, this is Samrat. I am the Chief Architect in the NEC's ProgrammableFlow division, where I lead mostly the solution architectures, working with different customers as well as the product group. And I have been in this since NEC started in the OpenFlow space. Before that, I have been coming from a research background in NEC for a long time in the area of networking and distributed systems. So my focus here is mostly in the software-defined networking architectures as NEC develops it, and then trying to find out its use cases both in enterprise data centers as well as the carriers, tier one. Plus, we are also delving into the whole OpenStack world and how it connects into the software-defined network space.
I'm Ivan Pepelnjak, and unfortunately, I've been in networking for too long, so I've seen almost everything there is to see, although some things still surprise me. I was first technical director in my company, and later I moved into what I call Chief Technology Advisor role. And lately, as you know, I'm doing a lot of blogging. I am developing webinars. I wrote a few books, and I'm doing some occasional consulting. On top of that, they persuaded me last year to start teaching scalable web application design course at my local university, and they managed to persuade me to do the same thing this year. My focus in the recent years, primarily large-scale data centers and network virtualization, and tied to that, network solutions for cloud computing, primarily infrastructure as a service cloud computing, and all the other things that sort of naturally come out of that, like scalable application design and things like IP routing or IPv6 with MPLS and VPNs. And now let's move forward, and we'll start with ProgrammableFlow principles of operation. The first thing we need to cover is the very basics of OpenFlow. If you need to know more about the details of OpenFlow, I would strongly recommend that you go and watch the OpenFlow webinar we did last year, because it does contain all the details what you need to know. The basic principle is very simple. In today's switches and routers, these devices act independently. Every single device in the network would run its own control plane, like this one here and this one here, and then they would exchange data between themselves, and every device on its own would then calculate the paths around the network and install those paths in its routing and forwarding table. So the networking devices are totally independent, they are on their own. Not so in OpenFlow. In OpenFlow, the control plane runs in a central controller. And that controller can be either an independent appliance or a server, or it could be built into one of the networking devices, and it would do all the control plane functionality. The devices themselves would only do forwarding and some maintenance function, like keeping track of which ports are up and down. Of course, if you want to do this, you need some sort of communication between the controller and those devices. That communication is done through TCP session, and we're using a special protocol called OpenFlow protocol. For security reasons, these TCP sessions could be encrypted with standard encryption. You can call it SSL or TLS. The same thing we're using with HTTPS. Now, the moment the device is connected to the controller knows that there are that many devices out there, and it can build topology of the network. Before going there, let me mention one other thing. You might want to establish these control sessions over the data path, so over the same links as the user traffic will be going through, but that's not very reliable, because if you hit a software bug somewhere, you could cut the controller off from the rest of the network. So it's better to have an out-of-band control plane network whose only functionality is to provide the connectivity between the controller and the switches. And so the controller builds the topology of the network in its software, and then the controller knows where, let's say, individual MAC addresses or individual prefixes are. So let's say we have a prefix B here, and on traditional switch, you would configure the subnet here on the switch interface. In the OpenFlow world, you would actually configure this prefix in the controller. So you don't do any configuration on the individual switches. You do the configuration in the controller. And then the controller, based with this subnet information or MAC address information and topology information, figures out what information needs to be downloaded into individual forwarding tables in the switches. And the forwarding tables could be simple layer 2 or layer 3 forwarding tables, which could match on source or destination MAC or IP addresses. Or some switches use richer matching tables called TCAMs, ternary content accessible memory. These are tables where you can do lookup based on a number of fields like source and destination IP address, source and destination port number, source and destination MAC addresses, and so on and so on. So TCAM gives you rich matching functionality that you can use to implement layer 2, layer 3, even layer 4 based forwarding. And so the OpenFlow controller would download the information into individual switches. And in our case, it would download the information that B is reachable here in this switch, that B is reachable over this link in this switch. And here you see the controller would know that this switch has 2 equal cost paths to prefix B. And so it would download 2 equivalent entries into this switch and thus enable equal cost load balancing. The whole OpenFlow network, and in our case, the ProgrammableFlow network fabric, appears as a single device to the outside world. So from the outside, it looks like a single switch with many ports, and we don't really care what's inside. All the forwarding behavior of this cloud that we can't see yet is controlled by the OpenFlow controller. In our case, this is the ProgrammableFlow controller from NEC. And anyone looking at this picture would quickly say, hey, but isn't the controller a single point of failure? And actually it is. And you know what you have to do when you have a single point of failure. You add another one. The same thing NEC did, and so in every resilient ProgrammableFlow network, you should have 2 controllers in a cluster. The cluster between them is established based on your configuration, more or less automatically. And once they work in a cluster, they constantly exchange data so that if one of them fails, the other one has all the information it needs to take over and continue managing the network. And like with any cluster, you need some sort of connectivity between the 2 controllers. And that's the role of the cluster interconnect network between the 2. And to make it fully redundant, the ProgrammableFlow controllers, which are actually appliances running ProgrammableFlow software, have numerous Ethernet ports to satisfy all the connectivity needs, among them 2 dedicated cluster interconnect ports that you use to connect the 2 flow controllers together, so that you always have 2 paths between them and a single link failure doesn't cause a split brain scenario. Now, going slightly deeper into the topology of the network, we build the actual physical network with OpenFlow enabled switches. There are some vendors that do switches that can only do OpenFlow. In NEC's case, the OpenFlow enabled switches can work independently, or they can be controlled from the central OpenFlow controller, which is the use case that we're interested in today. So you take a number of these switches, and the first thing you have to do is you have to connect them to the controllers, which is the role of the special OpenFlow control network. So you need additional traditional layer 2 switches to build the control plane network, and you have 2 ports on each controller and 2 ports on each OpenFlow switch, so that you can build 2 separate OpenFlow control plane networks, and actually you have an air gap between them. So if one of them fails, the other one will still be operational. A question from the audience based on the previous slide: if there are only 2 ports for cluster interconnect, how do you ensure high availability for network spanning multiple sites? I wouldn't use ProgrammableFlow for an OpenFlow network that would span multiple sites. I would have one set of controllers on one site and one set of controller on the other side, and then use traditional mechanisms to connect them together. Because remember, if you build a distributed OpenFlow network, then one data center depends totally on the availability of the controller in the other data center. If the links between the data centers go down, you lose one data center, not just the links. Next question: what about the latency of communication between the controller and the switches, and or the time required for the controller to figure out the forwarding tables?
Yeah, the latency is essentially only comes into play when you're trying to push a forwarding table entry into the switch. But as you know, the reactive nature of it is that delay just adds to the time to set up the flow. In the meantime, the packets are essentially still getting routed through the controller. So we don't have any sort of gap or missing forwarding point in this thing. But yes, it is true that the latency between the controller and the switch is important, and that's why typically they're in the same network. It's not like a controller you would place far away in the WAN.
The next related question is, why do we need the control plane network? So why do we need these extra switches? The problem is that if you program the OpenFlow switches through in-band means, then you can cut yourself off from the network. So it's safer to have totally separate control plane network than to try to program the switches through in-band communication. And by the way, keep in mind that this is a solution that was targeted primarily at data centers. You can assume that these switches are relatively close together and that it's not a problem to build a separate control plane network. Okay, and then we have the data network that is used to forward the user traffic, and this data network is fully controlled through the OpenFlow entries downloaded from the controller into the switches. And finally, there is the fourth network, the management network, which the ProgrammableFlow controllers use to communicate with the outside world. In the ideal case, you would actually build 4 separate networks for resiliency purposes. If you want to be on the cheap, of course, you can combine the management and the control plane network, but maybe you should keep all 4 of them separate. Now, you can build any topology you wish with the ProgrammableFlow switches. And the controller will figure out what the topology is. So you can build a ring, you can build a full mesh, you can build whatever you wish. But as it's always the case, it's optimal if you use a cloth or leaf and spine fabric to build larger fabrics. Because with that, first, you get equidistant bandwidth between all endpoints. And secondly, you have the ability to keep the complexity on the network edge and use high-speed, simple switches in the network core. Not surprisingly, NEC has two models of ProgrammableFlow OpenFlow switches, and one of them is primarily used in edge with gig ports toward servers or external devices and 10 gig uplinks. And this one has loads of OpenFlow, so the 7 or 10 tuple entries that you can use for fine granular packet matching or policy-based routing or what have you. And the core switch has 10 gig and 40 gig ports, but it only has 750 full OpenFlow entries, but you don't need them in the core. You only need layer 2 or something similar to pass the traffic between the edges. And recently, there's a third switch, and it's a virtual switch for Hyper-V. And this virtual switch is actually, as far as I'm aware, the first shipping third-party switch for the new Hyper-V environment, fully OpenFlow capable with lots and lots of flow entries, but that's easy to do because this is all done in software. And it supports over 1,000 virtual ports, so this would be the VMs, and 8 physical ports. So with the PF1000, you can actually extend the OpenFlow down into the hypervisors. And what this gives you is that the whole network, the physical switches and all the hypervisors, appear to the outside world as a single control plane, as a single management interface, and as a single device that you have to configure. And with that, you can then configure consistent end-to-end connectivity, and you can enforce the virtual networks because the ProgrammableFlow controllers control everything from a VM on one end to a VM on the other end. Now, I already mentioned that the OpenFlow controller can figure out whatever topology you're using in your network. And now let's see how that's done. Initially, the ProgrammableFlow controller has no idea what's going on. When the devices start connecting to the ProgrammableFlow controller, the controller starts building the model of the physical topology. So for every device, it adds a node in the model. But it still doesn't know how these devices are connected to each other. What happens next is there are special OpenFlow messages that the controller can use to figure out the ports on the device and the port status on the device. So the controller goes through the interface discovery portion of the process with every single switch or router and figures out how many ports that switch has. But it still doesn't know how those ports are connected to other switches. To figure that out, the ProgrammableFlow controller uses the same mechanism as routers or switches do in a regular network. It uses protocol to discover topology. Only in this case, the individual switches cannot do anything on their own because the control plane is in the controller. So this is the only place that has some intelligence. The controller has to tell individual switches that they have to send out packets to other switches. So for example, the controller would tell this switch to send out an LLDP packet over this port. There's a packet out OpenFlow message, and in the packet out, you specify which packet you want to send out through which port, and an LLDP packet is sent out through this particular port. And this other switch receives the LLDP packet, has no idea what to do with it because it has no local intelligence. All the control planes running here, don't forget that. And so the switch sends the packet through packet in message back to the controller. And now the controller can say, okay, I've sent this message out through one particular port, and it has been received through this other port on this other switch. So these two ports must be connected. And so it eventually builds the topology of the network. Now that we have the topology and we know where individual endpoints are, which we can learn through listening to, let's say, their broadcasts if we're talking about layer 2, we have to do some routing functionality. Let's say A is sending packets to B, and this first switch has no idea what to do with the packet, so you know what it will do. It will send a packet in message to the controller, telling the controller, I've received this and I really have no idea what to do. The controller would look at the topology of the network, figure out how to get to B. By the way, it will also update the MAC address table, so it knows where A is now. It will update its ARP tables, it will update its IP tables, and it will calculate the best path across the network. Now, this best path could be least cost path, or it could include some policy map. And the policy map tells you how to use various equal cost paths. So you might want to use one path for certain traffic and some other path for some other traffic. With that, you actually achieve policy-based routing. But you see, the point is that in traditional networks, you had to do policy-based routing on every single device. And here, you only configure it in the controller, and the controller takes care of all the rest. So the controller got the packet, it knows where B is, it figures out what the best path is, and now the controller downloads the flows to all the switches. So to go from A to B, this is how you have to go. And OpenFlow entries are obviously installed along the best path. Sometimes the controller might be able to pre-install the backup path as well. But sometimes that just doesn't work. For example, if this link over here fails, there is no way that a backup path could be pre-installed here because this switch cannot react to a link failure over here. What the controller has to do at that time is, after the link failure is encountered, it recomputes the topology and installs alternate flows into all the switches along the path. This one is for you, Samrat. What's the forwarding capacity of the controllers?
Yeah, the forwarding capacity of the controller depends upon the server and the NIC capacity. Our controller can scale very good in terms of processing the packets. So effectively, if you have good CPU and memory, particularly the memory and the good NIC bandwidth, so you should be able to forward almost into the 80% capacity of the NIC.
Next one, does clustering means adding clustering protocol between PFCs? If not, how is the persistency maintained?
Sure. So for clustering, the controller uses NEC's clustering technology, and as you perhaps know, NEC is a leader in the server space. So we use a special memory synchronization also, which means that all the states which is kept at any of the controller and the states reflect the flow table entries are synchronized at a memory level with the second controller, the backup controller. And what it means is that any controller, if it goes offline, the other controller comes up with the state space rapidly. That means there is hardly any delay or gap in terms of switching over from one controller to the other controller.
Which also answered the question whether the protocol between them is standard or proprietary. Then we have a number of questions regarding the control plane protocols. So how does the OpenFlow network interact with the outside world like OSPF or BGP? It doesn't. It uses static routing, and later on I'll show you in which use cases this is not a problem. Can this switch do LACP to servers? Samrat, I think the answer is no.
Yeah, what it provides lag, and you can set up load balancing based on IP hash or MAC hashing, but it does not provide the exact LACP in terms of the monitoring part of it. It takes care of link level. If link goes down, it will take over the other link, but I think it doesn't support the LSCP protocol as such.
This is what people would call static port channel. And in the virtualized environment, it might not even make sense to have port channel toward a server. So toward a bare metal server, it absolutely makes sense to do so. In VMware or Hyper-V environment, it might make more sense to have individual VMs assigned to individual uplink ports, and then the controller would sense that because it will see the MAC addresses coming from the hypervisor hosts.
One more thing here is in connecting any virtual VM or ESX or any of the hypervisor to the next level switches, even though we do not have the LSP, what we have is a multi-switch lag. I think you're probably going to talk about it later, that you can connect to more than one switches. So it takes care of not just the link, but the switch level failure as well.
There's another one. What about VMware?
Yeah, right now the VMware vSwitch does not support any OpenFlow control like, let's say, your Hyper-V switch or the OVS. So the way to use it, essentially, we can map the VMware vSwitch port groups VLAN into the ProgrammableFlow network, and that's something Ivan is going to talk about later. And that's the only way. It's basically like a legacy switch connecting into an OpenFlow network, where the legacy switch is the vSwitch does not participate directly with the controller.
Now, we have a number of questions regarding the flow entries and full flow entries. Okay. As you know, if you were reading my blog posts, one of the major problems of any OpenFlow solution is the flow scalability. What you have to do if you want to have a scalable solution is you have to do as much as possible on the edge and as little as possible in the core. This is exactly what a programmable flow controller is doing. So later on, you'll see how the virtual networking works, and you will see that we can do layer 2, layer 3, and layer 4 with policy maps or packet filters or traffic redirection. And actually, what goes on behind the scenes is that PFC is computing the optimal flows based on your configuration and downloading them into the ingress edge switch. So the ingress edge switch is doing most of the heavy lifting, and then it marks the packet in some cases. In other cases, the packet is forwarded through the network based on the MAC address. So if it marks the packet, think of it like MPLS. It does the classification, it figures out what the path across the network is, it marks the packet, it sends the packet across the network, and the only thing that the network has to do is just forward the packet along the path until it gets to the egress port. So all of the heavy lifting is done on the edge switches, which is why this thing scales, because the core switches don't have the full 5 or 7 or whatever tuple OpenFlow entries. The core switches just forward based on a few bits in each individual frame. And the other set of questions was about A and B and how we know where A and B is. In this particular case, I was assuming that B was previously known. If an unknown A is sending a packet to an unknown B, and they are both in the same layer 2 segment, then the only thing we can do is flooding, unknown unicast flooding. And yes, we can do it, and way later I'll show you how that's done. So I assumed here that B was known. The next set of questions was along the lines of, so does the first packet of every flow has to go to the controller? And the answer is no. Only if the controller didn't know about A before, then when the A sends the first packet, it goes to the controller. And at that time, the controller has to analyze the model of the virtual network to which A is connected. It has to figure out what happens to packets sent by A and downloads a number of OpenFlow entries into this edge switch. And obviously, the complexity of these entries depends on the complexity of your virtual tenant model. And we'll see later on what that is. So it doesn't mean that all the TCP SYN packets would be sent to the controller. Only when A is unknown is the first packet sent to the controller. And then if the topology of your network, virtual network, is simple, then the controller can pre-configure all these switches so that the new flows are automatically sent, let's say, between A and B. But of course, if you have configured some really weird packet filters, then maybe individual packets of other TCP flows will also go to the controller. And then there are a number of questions regarding IPv6 and other things and OpenFlow 1.0. As you already guessed, programmable flow switches are OpenFlow 1.0 switches, which means that the protocol on the wire is OpenFlow 1.0. Most of the things that we will be mentioning in the next slides, like IPv6 or QoS or flooding control, are vendor-specific extensions. The next question, can you mix OpenFlow controlled switches with traditional switches in the same network? The answer is yes, if the traditional switches are here on the edge and the OpenFlow domain is contiguous. Next question, also for you, Samrat, what's the number of flow modifications per second for the edge switch?
It is typically in the range of hundreds between the controller to the switch. The number is not limited by the controller capacity, but by the switch CPU capacity and the number of messages you can send from the controller to the switch. So effectively, raw is around the hundreds, but the maximum it can reach is like 1,000 flows per second.
And a few easy ones. Is the control network one large layer 2 domain? If I'm not mistaken, each control plane switch is one IP subnet, right?
Yes, the entire control plane, if you're talking about the secure channels, the management can belong to a one single layer 2 network.
And maybe, Samrat, just to give people a bit of a perspective, what's the biggest network you would build with the programmable flow switches?
Typically, a single controller can support up to 100 switches. The numbers comes by the number of MAC addresses, which it can support up to 200,000 and more. So that gives us an idea of the number of VMs you can connect to that network.
Another question, just to confirm, OpenFlow switches have to be contiguous? Yes. Next one, how does the switch and the PFC detect the break in the network? Now, there are two types of breaks. One is in the data path over here. And in this case, you can use the usual loss detection mechanism. And the other one is between the switch and the controller in the control plane network. And there you have to use OpenFlow or TCP keep alives. Interesting one, can the PFS 1000 work with a non-OpenFlow physical network?
PFS 1000 is just like a OpenFlow switch. It can only be controlled by a controller and can only participate in an OpenFlow network.
So you cannot use it as a standalone switch on Hyper-V?
You can, but it will be just like one switch point then, still controlled by the controller.
Okay, next one. Does controller of controllers exist to manage centrally distributed offices?
At this point, we have a way to manage multiple controller from a control and visualization point of view, but not where we are essentially creating a single controller domain from a state space. And that, I think, that is in the product roadmap.
The next one, does NEC plan to support OpenVSwitch in the future?
Right now, we support OpenVSwitch, but not as a product level support.
So it works, but it's not supported.
Exactly.
Oh, this is a good one. is the original packet in my scenario here on the slide queued on the first hop switch until the flow is propagated to all relevant switches? Actually, no. What's going on is that as the first packet is sent to the controller does two things at once. It starts downloading the flows into all the switches, and it sends a packet out message to the final egress switch to send the packet to the destination. So packet comes in, goes to the controller, is sent to the final switch and out. And that repeats until the flow entries are set up in the intermediate switches. So you have, if you wish, sort of process switching, as Cisco iOS fans would say. And then when the entries are downloaded, then you have the silicon-based switching. An interesting one on the interoperability. Can we use a lot of different vendors in our network and manage it with the one, let's say, ProgrammableFlow controller? So Samrat, what other vendors would you support?
So far, we have shown in public demonstration that we have worked or interworked with IBM Switch, Brocade, then Extreme, the Intel Fulcrum platform, at least what I know of. And there are other vendors which we are working with, which is basically not much about that we cannot. At this point, all we need is a support of full support of OpenFlow spec 1.0 to provide all the features which we'll be talking about in the next stage.
Okay, I think we already answered the question, can controller be distributed? I would say no. Even if you're running in a cluster, you still have to have them pretty close together. Question from Isabel, how about interoperability with other vendors' controllers?
Yes, so at this point of time, the OpenFlow Network Foundation, the standard body, has not defined anything how two controllers can interwork, but I hear that that is in the charter. So right now, a single controller can only control its domain, but a controller cannot talk to another vendor controller for peering or any other type of such functionalities.
Can an OpenFlow network have multiple controllers controlling different parts of the network? In theory, yes, but then you would actually build different OpenFlow networks, and you would have to interconnect them using whatever standard means of internet connecting networks you want to use. What are the measures taken to protect the security of the PFC? The first thing that is in place is the control plane network. So PFC is only reachable through the control plane network. And control plane network is totally isolated from the data network.
No, that is right. And also, in terms of accessing the PFC, it is over the SSH. And then one can, of course, add any other best practices to secure the PFC.
Can the controller make flow decisions based on link utilization?
Yes, it does. Flow decision, it does that because it uses the ECMP as well, and it can go up to 8-way ECMP. And in order to use the multipath with the 8-way ECMP, it actually does see the load in terms of the flows, and then accordingly maps new flows into new paths. So in this case, it's one of the scenario where the flows are deployed based on the load of the network.
We all know that, we build whatever physical topology we build, and we have whatever hypervisor solutions and virtual machines and so on. But what the customers actually want is something like this. Most applications today rely on pretty complex application stacks with multiple tiers that are linked together with layer 2 segments, routers, load balancers, and firewalls. And we have to emulate that somehow in the whatever virtual networking solution we are proposing. And this is how NEC is doing it. Their major concept are virtual tenant networks. And a virtual tenant network is an isolated network that is built logically. for individual tenants. And the tenant doesn't care about the physical infrastructure in the network. So that's why there are the clouds there. And the person configuring the virtual tenant network doesn't care about the physical topology in the network. So when you configure this virtual tenant network, you don't care about VLANs, at least not in the core. You don't care about trunking. You don't care about allowed VLANs. You don't care about spanning tree. You don't care about the core network at all. The only thing you're really interested in is how will I connect the tenant endpoints together? And there are two types of nodes you can have in a virtual tenant network, the bridges and the routers. They're all virtual, remember. This does not map into any physical device. This is a conceptual model that is used to calculate the flows that then have to be downloaded into individual devices. And by the way, the virtual routers can do IPv4 and IPv6, which, by the way, I think is more or less one of the first virtual networking products with full IPv6 support. Now, all these nodes have virtual interfaces. You have virtual bridge interfaces on the bridge, virtual router interfaces on the router, and external interfaces on the edges of the network. And finally, you have to add the virtual links that connect all of them together. And then you have to somehow map these edge interfaces to physical ports. And you could very easily say, I have this physical port, let's say on which a bare metal server is configured or a firewall is connected to it, and it maps straight into a virtual layer 2 segment. Or you could have another device here that has multiple VLANs on this trunk link, but the trunk link is a physical concept. We don't want to know about physical networking here. We are talking about virtual networks. What we need here is we are mapping a certain VLAN on a physical port to a virtual segment. And even though each virtual segment is associated with a VLAN, because internally we still need some identifier and VLAN is just convenient, we can do VLAN rewriting on the fly. So you could say I have VLAN 1 here on this particular link, but by the way, internally this is VLAN 1000. So we would use this manual mapping for external physical devices where you're not using any VLAN tagging with the external device, or in the case of overlapping VLANs. If you have the well-designed network in place where the VLANs are the same all over the place and trunking works as expected, then it's way easier to say, okay, you know what, I just have VLAN 100 in this segment, and whatever appears with VLAN 100 from anywhere in the network belongs to this segment. So this simplifies the configuration. And with this, every external port that you configure that can participate in this particular logical segment can automatically belong to that segment. And the VLAN membership has to be configured manually. So the trunk links have to be configured manually on the external ports with the prior software release. And now with PF1000, because we are controlling the whole thing, you automatically configure the VLAN membership with Hyper-V. And then there is the expanded VLAN mode, where we are still using VLANs, but VLANs only have local significance. So they are not the same end-to-end, but on an individual physical switch, you might have VLAN 100, but on another physical switch, you have VLAN 200, and it would be the same virtual segment. So you would use the expanded VLAN mode when you have overlapping VLANs. So for example, you have some traditional data center switches from some other vendor and they only support 256 VLANs and you need more. So you would have overlapping VLANs. You can solve that with expanded VLAN mode. Or if you need more than 1000 vBridges, so if you need more than 1000 VLAN IDs in the whole fabric, then you have to go for expanded VLAN mode. And then there's time to map these logical segments to the physical world. Remember, the bridges and routers, they don't exist in the physical devices. So although it looks like this thing here maps perfectly into this thing here, there is actually no match between the two. It's not like the edge switches would be layer 2 switches and the core switches would be layer 3 switches. This virtual network is mapped on the physical topology, as I explained before, in an optimal manner where the ingress edge switch does most of the heavy lifting on the external port, including things like MAC header rewrites for routing and TTL decrement for routing. So even though the virtual network looks like this, actually the whole functionality of a bridge, a router, and another bridge is implemented on the edge switch and downloaded from PFC as flow entries into this edge switch. So the packet forwarding across the network is always optimal. If you have two devices connected to the same physical switch, and even though they are in two different layer 3 segments, the packets will always flow optimally. And because TTL decrement is implemented, even traceroute works across virtual routers, even though virtual routers don't exist anywhere. Talking about the control plane, these things are still pretty simple. So on the bridging side, we have the MAC address learning plus static MAC addresses and MAC table aging. And on the routing side, we have IPv4 and IPv6 subnets with associated ARP and ND learning plus static entries. And we have static routes. No routing protocols yet. We do have DHCP relays, so if you want to use DHCP on the end nodes and the DHCP server is somewhere over here, the virtual router can do DHCP relaying. And then there are packet filters. On every single interface in the system, on every one of them, you can apply a packet filter, inbound or outbound. And these packet filters can do permit, drop, or interestingly, redirect. And remember, you can apply the packet filter here on the virtual router, but in reality, the packet filter would be applied on the ingress port on this switch. So whatever you specify, wherever you configure the packet filters, they are usually implemented on the ingress port of the ingress edge switch. The configuration syntax is very similar to what Junos has or what Cisco IOS has with modular quality of service CLI. First, you have a flow list that specifies the traffic matches, and then you have the filter list, which specifies which actions are applied to a particular type of matched traffic. And you can match on the expected things: MAC source destination address, ether type priority, and IPv4 and v6 source destination and port numbers. So you cannot build a real virtual firewall with this, but you can build access lists or packet filters. And here is a sample configuration syntax. We have a flow list which matches certain destination IP address, and we apply this on a particular interface on the bridge. Flow filter in, so this would be applied here. And if the packets from this host have this destination address, then we pass the packets, otherwise we drop them. A really interesting option is traffic redirection. Instead of dropping the packets, we can redirect the packets to some other device. For example, you might have a web proxy here, and in this case, we would match all traffic going to port 80, coming to this port with destination port 80, which means that this particular host is doing some HTTP request to an external web server. And we can redirect this packets to, let's say, transparent web proxy. But now the problem we have is that this transparent web proxy has its own MAC address, and it's only listening to its own MAC address. So we need to rewrite the destination MAC address to match the MAC address of the web proxy. And this is how we would do it. After this, all TCP packets going to TCP port 80 coming from this host would automatically land at the transparent web proxy. And you know what the use cases are. Either web proxies, as I already mentioned, or IPS or IDS, or even some baseline load balancing functionality. Thus, layer 2 and layer 3 address make sense in OpenFlow networks. Well, actually, what we have to do is we have to map the traditional networking concepts into this virtual tenant network so that we can figure out how to forward the packets. So from the pure OpenFlow perspective, we're actually matching on values in individual fields in the packet. So an OpenFlow switch doesn't care about layer 2 or layer 3 addresses, but the end user does. And so, yes, layer 2 and layer 3 addresses make sense from the virtual tenant network perspective. Can PFC program virtual firewall functionality? Well, not stateful. Stateless packet filters, yes. Stateful, no. How do I integrate the vRouter with external routers through dynamic routing protocols, etc.? You can't. At the moment, it only works with static routes. Does VTN deals with the resource sharing? If you mean link sharing, then absolutely yes. As I explained, the virtual tenant network is just a concept used by the controller to figure out what's going on. The controller then figures out what the best path is across the network and then installs the flow entries as granular or as generic as they need to be into the individual switches. So yes, it absolutely takes care about the resource sharing. What actually happens when controllers are lost, for example, from a bug? So if PFCs share memory, they could stop working together. Would the network still work?
If there is any such corruption or it goes into a wrong state, the switches can only work up till the floatables expire. But if it goes into a wrong state and it cannot create new floatables, then all the future flows will not be created. So it gives you maybe a little bit of time to restart or take it to the right stage.
So as long as the topology doesn't change, we are good, and we hope that the controller restarts in that time. What about the firmware upgrades to the PFC?
The version upgrade into the PFC or the controller actually can be done in a way where you do not have to have any interruption into the whole network. It is basically done by using the whole active standby, so where we make the standby primary and upgrade it and then take it to the next stage. So we have a totally non-interruption based migration path from one version to the other version in the network.
So a follow-up question to the previous one, will the network continue working as long as the topology doesn't change or as long as the MAC addresses don't age out? I would say whatever is first.
That's correct.
This is an interesting one. Do the program flows age and expire after certain timeout or only when they are reprogrammed from the controller?
It expires. There is an expiry timer, and you can set it to different values. But typically for robustness and also to ensure that the floatable size doesn't expire, the typical way is that you keep it for around 10 minutes or even 1 minute after there is no packet flow going on there. So if there is any flow which is idling for some period of time, then it automatically expires until a new traffic comes in where the controller goes and adds that floatable into each of the switches.
Another question, what about VLAN stacking or Q-in-Q? Can you use VLAN stacking on the edge ports, for example?
Typically switches provide that, but there isn't a functionality which can be driven by the controller at this point of time.
How to manage loops if the virtual topology of the VTN has redundant layer 2 paths? Can you have like 2 virtual routers in the virtual tenant network?
No, you cannot have more than one virtual router because essentially a single virtual router is enough to declare your requirement in terms of how many subnets you want. And if you look at it, it's a very much like a tree type of way of defining. So you cannot actually create a loop in that VTN design of it.
Here, yet again, whatever I'm mentioning are extensions to OpenFlow 1.0 because OpenFlow 1.0 doesn't really have a lot of quality of service built in. And what we can do with Programmable Flow Controller is we can do traffic classification And then after the traffic is classified, we can do 3-color policing. So the dual token bucket with committed and peak information rate and variable burst sizes. And based on the 3-color policing, we can do 802.1p marking or DSCP marking or packet dropping. And once you have 802.1p marking in place, you can start doing priority queuing in the physical switches, which is done by default because this is how 802.1q says you should do it. And additionally, you can configure different types of queuing or queuing based on different values directly on the physical switches. But what you really should be doing in a well-designed network is you set up generic QoS rules. So you say, I have this priority classes and I want to allocate this much traffic to this particular priority class. And then you configure that on the physical switches. And then you're done and you leave the switches alone. And you do all the rest of the QoS work through the ProgrammableFlow controller. And here is an example of traffic policing. So I'm matching web traffic, which is all traffic going to port 80. And then I create a policing profile where I match this. I meter with committed and peak information rate. Green action means I'm within the committed information rate, so I pass. Yellow action means I'm between the two, so I can apply some penalty, and penalty is set DSCP value or set 802.1p value or set a drop precedence. And after I'm above peak information rate, I drop it. And you can apply policing actually on the ingress external interfaces. Now you can configure it on vBridges or on the whole network, but this is a templating operation. So when you configure a policing profile on a vBridge, it's actually applied to every ingress interface connected to that vBridge. And when you configure a policing profile on a VTN, it's actually applied to every external interface of that VTN. You see, it's pretty easy to configure generic traffic policing. You apply it to a VTN as such, and it's automatically applied to every single port of that VTN. And by the way, if an external port is a VLAN on a physical interface, then obviously traffic policing works on that particular VLAN of that interface. Then there's traffic marking, and I already mentioned that you can do traffic marking based on the policing results, or you can do traffic marking with traffic filters. So we've mentioned the traffic filters before. Apart from the pass action in the traffic filter, there's also the set action where you can set different fields like DSCP marking. If you apply traffic filter on any interface anywhere in the network, remember that all this heavy lifting is done on the ingress switch. So in most cases, if you apply traffic marking anywhere in your virtual network, actually the marking takes place on the ingress switch and works and affects end-to-end queuing. This is something where the ProgrammableFlow Virtual Tenant Networks are totally different from what we are used to do in the physical networks. What about the difference in bandwidth? 1 gig in access versus 10 gig in core, and QoS metering. How does that work? Well, actually, you configure QoS metering on the ingress interfaces of the virtual tenant network. You could say, I have this physical device and it's applied to and it's connected to a layer 2 segment, and I'm applying an inbound policing on this particular external interface. So remember, policing is always applied to external interfaces. So in our case, it would be applied to this external port. Or you could apply policing to a layer 2 segment, in which case it would be applied to both external interfaces. So it would be applied to this port as well. Or you could have the automatic VLAN mode, in which case the controller is automatically creating vExternal interfaces as things appear. And in that case, the policing would automatically be applied to external ports to which these particular devices are connected. So you would never ever apply policing to an internal port. It's always on an external port. So the speed difference doesn't matter because you're always metering traffic coming directly from an external source. You know that layer 2 networks have serious scalability constraints. And it's not just the spanning tree. We're not discussing spanning tree here. The problem is that layer 2 forwarding relies on flooding of multicasts and unknown unicasts. And because the hypervisors, particularly if you work in virtualized environment, the hypervisors have to put their physical NICs in promiscuous mode, all the hypervisors will get all the flooded packets, so you will burn the hypervisor CPU. Unfortunately, people use a very common design where they configure every VLAN on every server port just in case, which means that every hypervisor gets multicast for every single VLAN, even if the hypervisor has nothing active in that VLAN. And some marketing people are promising you heavens on earth, and people writing standards are more realistic. They're saying, well, honestly, the current broadcast domains can support around 1,000 end hosts in an environment of around 100 bridges. This is straight from the Trail RFC. And if you have every VLAN on every server port, because of the amount of broadcast you're generating, you're actually talking about 1,000 VMs. So we definitely need some scalability tools. And the first thing, and yet again, this is an extension of OpenFlow. OpenFlow has nothing like this, is policing of flooding traffic. We are monitoring the internal ports this time. And if we're getting too much flooded traffic from the internal ports, we start to drop it. Remember, this is the external port, this is the internal port, so we would be monitoring internal ports only. And if A is sending broadcasts toward B, then this might be the potential monitoring points. And if different broadcasts are arriving to this switch, then they would be added together, so we are monitoring the aggregate of all flooded traffic. The match conditions are ignored, so we are only interested in flooded traffic. And we can either set a priority or drop it. So these are the two options. And by the way, this only works on the edge switches on PF5240s, even though in theory this would be the internal ports where you could do the flooding policing. You cannot do it if you use 5820s as the core switches. The question I got before was, okay, so how does an OpenFlow network handle unknown unicast flooding? For multicast and broadcast flooding, it's simple. When a virtual tenant network is configured and we know where the external points are, we can pre-configure the flooding trees like in traditional spanning tree. And the broadcasts and multicasts would be flooded along the spanning tree from every ingress switch toward the rest of the network, obviously controlled by the vExternal interfaces of the vTenant network. But what about the unicast flooding? Actually, the unicast flooding has to be done through the controller. So let's say A is sending a packet to X, and we haven't seen X before, so we have no idea where X is. The switch can do nothing else but to send the packet to the controller. And now the controller also doesn't know where X is. It hasn't seen it before. So it has to emulate layer 2 behavior and flood this to all the other vExternal interfaces on the same virtual tenant network with packet out messages sent to all the other switches participating in this virtual tenant network. And so you are actually doing unicast flooding through the control plane, which is a bad idea. But this is how it works, and there's not much we can do. However, we can apply shaping on ingress OpenFlow switch. Yet again, this is an extension to OpenFlow, and this prevents too many unicast packets from being sent to the controller, so at least you are protecting the controller from the unicast flooding, and you are protecting the communication channel so that you don't saturate the SSL session with unicast flooding. You probably know that one of the major sources of unicast flood are the situations where the ARP timer is bigger than the MAC aging timer and you have unidirectional traffic. MAC addresses expire in the controller and in the switches, and because A is only sending the traffic to B and not receiving any traffic back from B, so B could be, for example, syslog host. No one knows where B is, but because the ARP timer hasn't timed out yet, A would not send another ARP request, so no one knows where B is. And we are back to unicast flooding. And you can configure ARP snooping and ARP refresh on the ProgrammableFlow controllers. ARP snooping is obvious. All the ARP requests go also to the ProgrammableFlow controller. It has to listen to ARP requests anyway, so that it can answer when someone is asking for the MAC address of the virtual router. And so with ARP snooping, PFC now has complete IP to MAC visibility. And when someone is sending packets toward B, and B is an IP destination, but its MAC address is unknown, then PFC can send an ARP request for B. It knows B exists because it has complete visibility, but it doesn't know where B is because the MAC address aged out, but it can trigger an ARP request, and so B will respond, and now we know where B is. So with this, we can get rid of most of the anomalous unicast flooding, but of course, if someone wants to configure something like Microsoft Network Load Balancing, where flooding is built into the system, then there is nothing you can do. Is ARP also multicast? Well, we handle broadcasts and multicasts the same from the flooding perspective, but obviously PFC would only listen to ARP requests, and with OpenFlow you can match on ARP packets specifically. Does it mean we can build some rules to manage the multicast trees? So Samrat, can you specify how the multicast tree will be built, over which particular physical links it will go?
PFC can proactively or does proactively build both the broadcast and the multicast trees, and it is done actually in the time when the VTNs are getting deployed into the network. And then after that, based on the matching criteria on the multicast address space or the broadcast address space, they can be routed to the trees. Typically, these trees are shared trees, which essentially connects the switches and the ports on that particular tree.
Is there no hybrid mode in the non-intelligent forwarding devices to start using ARP and normal protocols if PFCs suddenly break? No, you can't have the virtual tenant networks in the PFC and then revert to whatever if the PFC should break, because that could create security problems. Obviously, you have to do some initial configuration on the individual switches. And either you do it through CLI or you do it through DHCP, depending on what switches support. If nothing else, you have to configure the IP address on the control plane network, and you have to tell the physical switch that it has to connect to the OpenFlow controller. And then all the rest is configured through PFC. And PFC has 4 major configuration mechanisms. You can use CLI, or you can use GUI. And there's a GUI client for Windows, and there's a web-based interface. So you can have either a standalone Windows application or a web-based interface. And then there's the REST API, so-called Web API, and you can either use JSON or XML format, whatever you prefer. And there is an OpenStack Quantum API. And the functionality of all this is very similar from what you can do, only the presentation format is different. So here are a few CLI examples. How do I connect a virtual bridge with a router? First, I start the definition of a virtual tenant network, and then I start the definition of virtual router. I have an interface here with an IP address. Then I have a virtual bridge, which has another interface, and then I have a virtual link, which links this bridge, this interface on this bridge, with this interface on the router. And so on, and so on, and so on, and so on. You configure the virtual tenant network, let's say in this case, through the CLI. Or this is the Web API version of the same thing. In Web API, you're doing post requests through HTTPS to the PFC. These are the URLs you would use in your calls, And this is the JSON payload that you would be sending to the web server. So you see, for anyone who is familiar with REST programming, this is really a piece of cake. And if you don't like JSON, you can use XML. You only change the suffix in the URL and you can send XML data to the Programmable Flow controller. The same thing works for querying. So here I've shown how you configure individual things. You can use other API calls to get physical topology, to get the logical topology, to get the configuration, and so on, and so on, and so on. So you can actually query PFC and get the physical topology of the network, or you can get the virtual topology of a virtual tenant network. And as one of the attendees just remarked, it does make the whole thing open to an external orchestration system, which can use the REST API for either configuration or visualization needs. And one very popular case of an orchestration system is OpenStack. What we have now with the new release of ProgrammableFlow is the Quantum plugin, which connects to the PFC web API server. So we can now use either GUI with native API or whatever cloud orchestration software that you write yourself, or OpenStack with Quantum plugin, and then you have the OpenStack API. And Quantum also works with the other OpenFlow controller from NEC, the open source one. And here down below, we have the virtual tenant networks of PFC. So you can use PFC today if you're deploying OpenStack, and it will configure the network for you. Can you push individual flows from GUI to the switches?
It does not provide interface for individual flow level, as the VTN is the only interface you have, but there is a low-level interface to the controller you can use for pushing individual flows. But in that case, you would not be able to use the VTN, because in that case, that conflicts. So you have to use either the VTN way or directly OpenFlow style flow injection.
So you can use low-level flow injection, but in that case, you can't use VTNs. As I mentioned before, Programmable Flow Controller currently does not run any control plane protocols like spanning tree or routing protocols, which means that it's simplest if you can integrate this OpenFlow fabric with external networks on layer 4 and above through firewalls or load balancers. This would give you ideal layer 2 and layer 3 forwarding within the fabric. It would give you single configuration management and provisioning and single control plane entity, but you wouldn't have to run any protocols with the external network, because here you would have a demarcation point through firewalls or load balancers. Typical deployment scenarios would obviously be either private clouds or mid-size public clouds. Why am I saying mid-size? You've heard before, a reasonable number of switches is around 100. Or you could build Hadoop clusters with this. Or this might be a perfect use case. Turnkey systems where you want to ship a whole data center in a box to a customer, and you don't want the customer to have to deal with the physical connectivity and configuration of the switches. So you just use a programmable flow fabric and you give the customer visibility through the management interface. Talking about this deployment, there's an interesting question from the audience. Can the user configure the complete VTN, or can he only configure virtual bridges, routers, and their links? What you can configure on the VTN level are, as you said, virtual bridges, virtual routers, links between them, and connections to the outside world. So you could say, I have this external interface that goes into this subnet on this physical port. The administrator can configure how a virtual network topology should look like. How that topology is implemented on the physical devices is a different story, and that's the value add of the PFC. The other thing you can also do is you can specify over which paths you want certain traffic to flow, so you can implement some sort of policy-based routing within a VTN. The other ideal use case would be traffic steering. So if you want to send some traffic to IDS, IPS, or if you want to do service insertion, then the traffic steering capabilities of PFC would be ideal. Or you can use this to block denial of service attacks within the fabric. So if someone from an external IP address is attacking you, you can easily use traffic steering based on source IP address and drop the traffic or send it to an IDS for inspection. And finally, what I really like, extended OpenFlow that ties together the virtual and the physical switches. The whole cloud as appliance, together with the hypervisors, appears as a single configuration, management, and control plane entity. And because PFC has more features than a typical hypervisor switch, you could easily implement things that we are wishing for and asking for and never getting from the hypervisor vendors. Private VLANs we do have. Source, MAC, and IP address checks, well, we have them in some cases, and usually we have to configure them. And you can implement the NIC level packet filters on individual VMs straight from the baseline PFC functionality. Could it be reasonable to deploy ProgrammableFlow within Metro network to provide VTN services to business customers?
It may make sense. The only thing is that if you can deploy using OpenFlow switches, then you can definitely provide a sort of a multi-tenant B2B network where people can come and create their own network and ways to connect to their external gateways.
Oh, related to this particular slide, how many PFS 1000 switches can be managed by a PFC cluster?
The number of PFS actually builds on the number of switches, and the total number is around 100 under one controller.
Is it possible to write a GUI that can curl to the REST API to push the flows in the switch?
Yes, absolutely.
So why would anyone want to do that is a different story, but in theory, yes, it can be done.
In practice also it can be done.
But why would you do it?
Might be a custom application requirement.
Okay. Question that goes back to the very beginning. Does the control plane network have to be physically separated, or can you configure VLAN separation on your data plane and use that for control? At least on the switches, you have to use separate ports for the control plane network, right?
Yeah.
And personally, I would not use an in-band network to control the switches.
That is correct.
How do the virtual interfaces report error statistics from the underlying physical interfaces? If you have multiple external interfaces on a single physical interface and you have errors, how are those errors reported and where are they recorded? Or do we have to use SNMP with physical switches to get them?
So essentially it is about in the virtual interfaces connecting to a physical interface and any of the virtual interface failing?
I have a number of virtual machines connected to a single physical port, and I'm getting errors on that physical port. So where will I see those errors?
The controller will see the error from a physical port level, and that's one of the reasons you can always use NIC teaming with the controller, with our switches, so that if any error happens or any link goes down, it can move the traffic to the other link. Is that what you're looking for?
So actually the controller will see the interface errors on the physical interface, and then I guess you can extract that information from the controller with REST API.
Absolutely. You can monitor any port level status and information from the REST APIs.
Then there's a question whether ProgrammableFlow supports NetFlow or SFlow for monitoring purposes.
Yeah, it supports the normal switches can any switches which supports SFlow can be pushed to the management, but also along with it, it supports the OpenFlow based monitoring on packet counts and flow-based traffic monitoring.
So you can get the traffic counters from OpenFlow entries, which is actually what you're looking for, right? It can be equivalent to NetFlow.
Yes, and sometimes it says that because the counters are not sampled, you are essentially getting all the values. The switch is counting every packet. You have more accurate information from the OpenFlow statistics.
Yeah, so you are actually getting down to the accuracy of NetFlow, not the estimation of SFlow, right?
Yeah, that's right.
What, if any, SNMP management is supported by the PFC?
PFC does not, because the PFC's control is only using the OpenFlow protocol. But the switch can definitely, our switches supports SNMP based monitoring.
So you could use SNMP if you wish, and you can probably run it over control plane network from a third-party network management station and monitor switches through SNMP. And if you want to extract information from the programmable flow controller, you have to use the REST API.
Right.
In general, does PFC care about health of switches like ports going up and down and in-out errors and temperature levels and so on? Or do I have to do that with SNMP separately?
PFC does monitor some of these, like for example, link status and the switch status. And then it also uses those things to reroute traffic in case of any of the problems happen, transient problems or long-term problems. But it doesn't use all the information for such things like you're saying, like temperature and many other such parameters.
We were discussing, how the paths could be selected based on the link utilization. And here's the question: how does the controller know what the current link utilization is?
Controller has two levels of information. One is how or what flows are going through each of the path, because it controls the flow table entries. And the second, it also knows the actual value of the traffic by monitoring the counters from the switch.
Okay, and there is an easy one. What about FCOE? I would say no, because the whole thing is not lossless.
It's a very good question. You're right. It is not providing any particular control mechanism, but you can create a lossless path into the network by the policy-based routing and the QoS policing.
So with QoS policies on the physical switches, you can build a lossless path.
That's right.
And once you have the lossless path, then obviously you can run FCOE over it. And then we have at least two different people asking about when will the switches support OpenFlow 1.3?
By the midsummer, not exactly the dates are known, but somewhere in that time frame.
And then we have a few more or less commercial questions. How can I get the documentation or configuration guide?
All the information is available in the NEC Corporation of America SDN site.
Oh, by the way, let me move forward to the next slide. This is the contact within NEC. And if you have any follow-up commercial or technical questions, please contact Robert. What would be the best practice bandwidth for the out of band links for the control plane? It's 1 gig, right?
Yes, exactly. The bottleneck is hardly in the network. As you know, the bottleneck is essentially in the switch CPU bandwidth.
Then there's a question: aren't the switch entries deleted after timeout, so can counters be used to determine link utilization? Well, actually, when an OpenFlow entry is deleted, the message is sent to the controller with the current value of the counters, so you get those values. Follow-up question to OpenFlow 1.3: how many proprietary features will remain after you move to OpenFlow 1.3?
I'm not exactly sure. Strategy is to add in features in following the standards which is coming up. So while we are trying to put the 1.3, we're also adding many new features into it. So there is always going to be a lead between the features which NEC has added into that versus what is the standard body has make it public or official.
what is support for PFC? So I guess based on your previous answer, if PFC means priority flow control, not programmable flow controller, you have to configure it on the switches, right?
Yeah.
And the follow-up question is, if I go and configure priority flow control on my customer production network, does NEC support it?
Yes, you can do it, and typically that's the way you go, that you can have your queues be configured and then use the queuing policy to mark packets and then control how the queuing behavior takes place at the egress.
I think we answered this question, but nevertheless, you need to set up these OpenFlow switches to communicate with PFC. How is that done? Well, that is usually done through the CLI directly on the switches, and you have to configure the IP address of the switch, you have to configure the default gateway, you have to configure the IP address of the OpenFlow controller, and a few other things. Are there any plans to have these things automatically configured, like through DHCP, for example, and then boot P server or something?
Yes, there is. As you know already, that one of the other big configuration part has already been automated, which is the VLAN configuration at port level. So right now, every step we are taking in the new releases, we are trying to reduce any number of configuration which needs to be done at the initial stage in the switch. So definitely that's in the plan.
How is the controller calculating the best path for the forwarding packets to the destination? It's doing the same thing as any routing protocol. You have the default cost of each individual link, different obviously for 1 gig and 10 gig links, and the controller is taking the least cost path. But you can also manually change the costs of individual links, so that you can prefer some paths and use some other paths as purely backup. And then there is the policy map, where if you have equal cost path scenarios, you can map some traffic over some paths. So for example, you can say the backup traffic goes over one set of links and the user traffic goes over a different set of links. Then there is another one. Since there is no spanning tree, how is unicast flooding controlled and loop prevention achieved? The unicast flooding is done through the controller, so there is no way a loop could be introduced anywhere. How many ECMP paths can be used at the same time?
8.
From the convergence perspective, how quickly would a programmable flow fabric converge as compared to, let's say, RSTP?
We have seen around 100 to 200 milliseconds, and that's because the paths are already pre-computed and established, so it is more or less like a switching between paths.
That's the usual problem. You first have to detect that the link is down, and then the conversion has to kick in, and you just switch over to the second path.
That's right.
Putting data packets through the controller seems like a poor design decision. What is the need for this? You see, that's how OpenFlow works. That's how traditional routers and switches work as well. So if you don't know what to do with the packet on the hardware level, the only thing you can do is you either drop it or you punt it to the CPU, and then the CPU can decide what to do with it. And it's exactly the same thing here, only the CPU is not resident in the device. The CPU is actually the OpenFlow controller. So there are loads of benefits of using an OpenFlow controller, and there are a few drawbacks, and having to send the unknown data packets through the controller is one of them. Any plan to have some fast failure detection comparable to BFD? So let's say 10 millisecond or faster convergence.
At this point of time, like you rightly said, the total time is essentially dependent upon the detection time and the new flow switching time. So there is not any type of delays happening in the controller side or any other side. So that's the minimum delay you're talking about here.
Could controller take latency into account when calculating the best paths? So my naive answer would be that since we are talking about pretty local setups, latency doesn't really come into account, but are you doing something there?
So there is a way that you can create custom ways of using the routing there. And the way to do that is that you can monitor the information about the network to the REST interfaces, and then use that to dynamically change the link weight, and then use it on the least cost routing way. So even though it is not comes default in the programmable flow, but as you can see, it is very easy for someone to build any type of custom routing based on any dynamic metric on top of it.
For a fully configured 100 switch network, what speed should the control network be? Is 1 gig enough, or shall we go to 10 gig?
No, like you rightly said, the 1 gig is actually good enough. The only reason because the bottleneck is essentially in the switch CPU speed. So a 1 gig network is almost enough to support that switch, which is basically 100 messages per second from each of the switches.
The question is, so do we maintain a primary flow and a backup flow to achieve faster convergence, or are flow built on the fly during convergence? Now you see, there are different scenarios here. So let's say we are looking at the flows in this particular switch. Now in this particular switch, you could set up flow A pointing here and flow B pointing down here. And so when this link fails, because this is directly adjacent to the switch in which the flow is configured, this flow can be immediately removed and the alternate flow activated. However, if some other link fails, so you have the primary flow pointing here and the backup flow pointing here, and now this link has failed. This switch cannot react on its own because nothing has changed for this particular switch. So in this case, the OpenFlow controller has to reprogram this switch so that it stops using the path which is broken, but not here. The problem is that the path is broken somewhere else.
I want to add a little bit on that. So the paths are not computed on the fly, and they are pre-established. And it is a path level switching which are happening. So that's a good point, Ivan, you're saying that, in typical router, because it's a distributed, so every router is trying to figure out from his own local way that if I have a backup path or not. The good part here is that the controller is seeing it as a path end-to-end from ingress switch to the egress switch. So anything which breaks down in the path, it basically pushes it to the second backup already established ingress to egress path.
What would be a metric that would decide controller placement in the data center? So where would you put the controller in the data center?
I'm not so sure the placement objective, but the only requirement we have is that you have a ideal situation is that you have a local area network which connects all the switches to the controller.
Because you have that local area network that will put some physical restraints on the network, and that would then dictate where you want to put the controller, right?
Yeah.
What would be the killer scenarios for PFC?
If we look at it from scenarios of application, the most important part is automation, because it creates this virtual tenant model which totally decouples from going into the deeper level of how to manage, configure, run, switch network. The model essentially creates a much better way to expose APIs that can be used with different tools, orchestration engine, appliances to create any type of smart, richer type of ways to define network and automate network. It is, I think, is a more of a tool to bring people to come in and create different solution, as opposed to specifying that this is the only solution or the set of solution we can do or not.
If you have questions after watching this video, send a tweet to @iOSHint or send me an email using contact form on ibspace.net, where you'll also find information about other data center webinars. For all commercial questions and programmable flow evaluation requests, please contact NEC.